In the previous class, we derived the area Mach number relationship for flow through a varying area passage. In the next module, we are going to look at mass flow rate through So, here we are considering a passage in which the flow is choked at some location. So, that means the flow has reached the sonic state at some location in the middle. For example, this can be a convergent divergent nozzle which looks like this, and we can say that the flow is choked at this location. Remember, we showed earlier through the area velocity relationship that in such a passage, if the flow chokes, it must do so at the point where the area of cross section is a minimum. Okay. So, for example, in this case we may reach the sonic state here, and once the sonic state is reached, we wish to find out what is the mass flow rate through this. If the sonic state is not reached, then there are other ways of finding out mass flow rate, but for most applications we are interested in the mass flow rate when the passage is choked, because the sonic state is reached at the throat. The flow through the nozzle is said to be choked. So, the flow through the nozzle is said to be choked, and we wish to derive an expression for the mass flow rate through the nozzle or the passage. Okay. So, I start by writing my m dot. M dot is nothing but at any section, m dot is rho times u times area at the section. And if I write this in terms of known quantities, for example, I can multiply and divide by a rho naught and write this as rho over rho naught times rho naught, and the u I can write as the Mach number times square root of gamma RT, right, speed of sound, and the a I can write like this, a over a star times a star. Since the flow is choked, I can write this as a over the cross sectional area where the flow chokes times a star, right. So, a star is the location where the Mach number reaches 1. Now, I can take this static temperature and write that as T over T naught times T naught. So, if I expand this equation further, I can write this as rho over rho naught times m times square root of gamma or T over T naught times T naught, all within the square root, times a over a star times a star. Notice that rho over rho naught is known to us as a function of Mach number, right. We know the relationship. T over T naught is also known to us as a function of Mach number. A over a star is also known to us as a function of Mach number, because that is what we derived in the previous class, area Mach number relationship. So, if you rearrange this expression, I can write the rho naught as P naught over RT naught. So, let us go ahead and do that, P naught over RT naught times square root of gamma or T naught times a star times rho over rho naught times square root of T over T naught times a over a star. Right. These three quantities are functions of Mach number alone. So, if I go ahead and substitute these functions and then simplify, I end up with the expression for m dot, which looks like this. So, m dot is equal to P0. Remember, we said using our area velocity relationship that if the flow chokes, it must do so at a point of minimum cross sectional area, right. So, I can replace this a star with a throat, right. So, I replace the area a star with a throat. So, P0 times a throat divided by square root of T naught times we have another quantity here which we write like this, gamma over r times 2 over gamma plus 1 to the power gamma plus 1 over gamma minus 1. So, this is the expression for mass flow rate through a choked passage. Okay. The expression that we have derived here is an extremely important expression in gas dynamics. This appears in many applications. In fact, this controls the operation of many devices which handle compressible flow. Okay. The probably one of the most important or most remarkable things about this expression is what?
Depends on stagnation values only.
The most important or most startling aspect of this expression is that no exit quantities or exit pressure is involved in this, right. This depends only on the upstream stagnation pressure, throat area, and the quantity inside this depends only on the nature of the gas, right. That is the most remarkable thing about this. So, what this tells you is that once the flow is choked, we cannot control the flow by adjusting the downstream conditions. Once the flow is choked, I can adjust conditions or mass flow rate only by adjusting these quantities. For example, I can change the throat area, I can change my stagnation pressure, or I can change my stagnation temperature, but not any of the downstream quantities. That is the reason why we said that the sonic state is a very important state. Remember, we achieved the sonic state here. So, what this tells me is once I achieve the sonic state here, I cannot control the mass flow rate by changing things downstream. The flow will be completely oblivious to whatever changes that are taking place here. If I want to change the mass flow rate, once it is changed, I need to change the stagnation pressure here or the stagnation temperature, or I can also change the throat area. Okay. So, let us write that down. So, this is independent to put it in a slightly different way, if for example, I am trying to control the flow by adjusting conditions downstream, I can do that up to a point. I can continue to do that up to a point, the point being attainment of the sonic state. As long as I do not attain the sonic state, I can control the mass flow rate by adjusting conditions downstream. But once I attain the sonic state at the throat, I can no longer control the flow by changing conditions downstream. That is what this says. In other words, this is the maximum mass flow rate that can be achieved by controlling the downstream state. This is not the maximum mass flow rate. This is the maximum mass flow rate that can be achieved by controlling downstream. Yes?
So, by changing downstream area, we can change mass flow rate also.
That does not appear here, right? I mean, if you change this area, then the flow is not choked, right? Then you will see exit quantities appearing here. If the flow is not choked, for instance, same situation, if the flow is not choked, then we need to specify the downstream static pressure also, and we can control the downstream static pressure to get the mass flow rate. That is also possible, correct? If, for example, you look at that situation. So, if the flow is not choked, then the downstream static pressure, or I can write this as exit static pressure. We are going to discuss these concepts next, but we can discuss them now, that is not a problem. The exit static pressure is equal to the ambient pressure, right? Then mass flow rate through the nozzle in this case can be written as m dot equal to rho e times ue times ae, where the subscript e refers to exit conditions. right. We can rewrite this in the same manner as we did earlier. I can write this as PE over RTE, and UE itself can be written as ME times square root of gamma R TE, and I can leave AE as it is. Exit area is known. Okay. Since the exit pressure is known, stagnation pressure is also known, and the flow is isentropic, right. Since PE and P0 are known and the flow is isentropic, this means I can get my exit Mach number by using the isentropic relationship, right. So, this means that P0 over PE is equal to 1 plus gamma minus 1 over 2 times ME square raised to the power gamma over gamma minus 1, right. P0 is known, PE is known, so I can calculate ME. Once I know ME, exit static temperature can also be calculated, right. T0 is known, right. So, for example, so from this I can calculate ME can be evaluated. Once ME is known, other things can be evaluated. So, TE can be evaluated from this relationship. T0 over TE is equal to 1 plus gamma minus 1 over 2 times ME square. T0 is known, so TE can be evaluated, and once I know that, notice that I can now evaluate the mass flow rate through the nozzle. This is if the flow is not choked. Once the flow is choked, the exit pressure is no longer sensed by the flow, which is why we go to this type of a situation. Okay. So, once it is choked, any further change in mass flow rate has to be achieved only by changing these quantities. Okay. So, the exit pressure appears in all these equations. Notice that the exit pressure is the key here, because we use the exit pressure to get ME. Once I get ME, all the other quantities can be evaluated. Once the exit pressure disappears, then I no longer have control over the flow from the downstream side, right. So, let us if you come back to this expression now, what we are going to say now for this expression is that this m dot is the maximum mass flow rate that can be attained by controlling the ambient pressure. This is probably one of the most poorly understood concepts in quasi one dimensional flow. Normally, it is said that this is the maximum mass flow rate that you can have in the nozzle. That is not true. This is the maximum mass flow rate you can have if you are trying to adjust the flow from downstream. Obviously, if you look at this expression, you can easily see, that even after if it is choked, even after the flow is choked, if I increase my P naught, I can get more mass flow rate, or if I decrease my T naught, I will get more mass flow rate. So, the maximum mass flow rate that can go through a nozzle, what is the limit on that? Unlimited. There is no limit that the mass flow rate that a nozzle can pass. If I am changing P naught and T naught, if I am changing PE, then this is the maximum that I can achieve. That is a very important point. So, this is the maximum mass flow rate that can be attained by controlling downstream pressure. If I am controlling stagnation pressure and temperature, I can have any mass flow rate that I want. But some other adjustments will take place, which is what we are going to discuss next. Okay. And you also remember from your from our discussion of normal shocks, flow with heat addition and flow with friction, right. If there is a loss of stagnation pressure upstream of the nozzle, then the mass flow rate that can go through the nozzle is also reduced, right. If there is a pipe, long pipe, then there is a loss of stagnation pressure, which means m dot becomes less than what it can be. In fact, if there is a heat addition before the nozzle, That is even worse, because heat addition, what does heat addition do? It increases T naught and it decreases P naught. So you can see that this increases, which reduces the mass flow rate, this reduces, which also reduces the mass flow rate even more, right. So heat addition ahead of the nozzle is actually a very, I won't say detrimental effect, causes the mass flow rate that can go through the nozzle tremendously. This kind of application is important, as we will see later when we talk about afterburners. In afterburners, you add heat before it goes to the nozzle. So this is an extremely important point for afterburner design. The reduction in mass flow rate is actually much higher if you add heat before the nozzle, because of the double effect. This increases and this also decreases. Okay. We will actually have an opportunity to revisit this expression for mass flow rate many times during our discussion as we go along. This is an extremely important discussion, because what this tells me is that this is the mass flow rate that is going through, and in some cases when you have multiple throats, this expression will determine what flow solutions are possible downstream. For instance, we said that the nozzle is insensitive to downstream conditions. As I keep changing downstream conditions, this kind of thing, mass flow keeps coming through. At some point the imbalance may be so much that you can have very strong changes taking place in the flow field. Okay. That also is something that we will discuss as we go along. Okay. This is an extremely important expression which you must remember. If not the functional form, if not the exact form, you must definitely remember the functional form. P0 A throat divided by square root of T naught. Okay. All right. Now we are going to look at flow through a convergent nozzle. So we have, let us say, a convergent nozzle like this. Let us label this inlet as 1, this outlet as 2, and let us say that the ambient, we say that the ambient pressure is P ambient and the stagnation conditions are known. When you have a nozzle like this, we can establish a flow through the nozzle in two different ways. One way is to pull the flow through the nozzle. So how do we pull the flow through the nozzle? We keep changing the ambient pressure to pull the flow through the nozzle. The other way is to push the flow through the nozzle. We do this by changing the stagnation conditions or the stagnation pressure. Keep increasing the stagnation pressure, that will push more and more flow through the nozzle. Changing the ambient pressure will pull the flow through the nozzle. Okay, these are the two different ways in which we can establish the flow. Let us see what happens as the flow goes through. In each one of these cases, what is the change of state, for example, along the length of the nozzle as we do this. Okay, that is what we are going to see, and we are going to actually illustrate this on a TS diagram. Let us start with the first one. We start with the first one. So we start by pulling the flow through the nozzle. Let us say that the inlet state is over here. Let me do it like this. So this is 1. Let us say this is T1 and this is P1. And let us say that this is my T01 and this is my P01 and this is my stagnation state 0, 1. So this is my inlet state and I have shown the stagnation state also. Now the ambient pressure, in this case we are going to change the ambient pressure, right. So corresponding to this T01 I can evaluate a T star, right. So let us evaluate a T star. Let us say that this is my T star and you know that T star corresponds to m equal to 1. Anything below T star we know that it is a supersonic state and anything above we know is a subsonic state. And of course once I know T star I also know my P equal to P star because this is the sonic state, right, that is the sonic state. So now what I do is let us say that I lower the ambient pressure a little bit less than P1. Okay. So the ambient pressure here is just a little bit less than P1. So the flow, we establish a flow and when it comes out with a certain velocity, and remember this is a converging passage, Mach number is subsonic. So we know from the area velocity relationship that the velocity increases, probably not to a sonic value for this value of ambient pressure, but the pressure decreases, velocity increases, temperature also decreases. So we probably will end up something like this. So this may be our so for this value of ambient pressure our state 2 is going to be over there. Okay, so where we have lowered the ambient pressure a little bit from the P1, right. So the flow happens like this. So you can see that the same stagnation condition U2 is going to be more than U1, right, because this distance, what is this distance? U2 square over 2Cp, right, that is this distance. So U2 has increased, pressure has decreased, temperature has also decreased. So it has gone through an expansion process, isentropic expansion process from state 1 to state 2. Now if I lower the ambient pressure a little bit more, right, I can get more flow to go through the nozzle. So let us say that I lower the ambient pressure something like this, right. Now my state 2 will come here. The flow accelerates some more, exit velocity increases some more. So as I keep lowering the ambient pressure, if I do this some more, then I get my ambient pressure to come to this value, right. P2 once again is equal to P ambient. As I do this, P2 is equal to P ambient in all these cases, correct. Now if I finally lower my P ambient to a value equal to P star, right, we know the value for P star, right, we know the isentropic relationship. So P0 over P star is equal to 1 plus gamma minus 1 over 2. We set m equal to 1, so this raised to the power gamma over gamma minus 1, and for gamma equal to 1.4 this comes out to be 1.8929. So if I know my stagnation pressure and I lower my ambient pressure to a value equal to this, then the exit velocity reaches the speed of sound and the exit state becomes the sonic state. So the flow expands all the way from here to this state. So this becomes the exit state at this point, and the pressure is equal to P star, the temperature is also equal to T star. Remember, T star can also be evaluated in the same way. So T star is equal to 1 plus gamma minus 1 over 2. right. So, this is nothing but gamma plus 1 over 2 and this is equal to 1.2 for gamma equal to 1.4. So, at this point the exit pressure is still equal to ambient pressure and the ambient pressure itself is equal to P star corresponding to that value of stagnation pressure. Okay. So, when we attain this state, so corresponding to this state, let me write it here. So, corresponding to this state, P ambient becomes equal to P star corresponding to the given value of P naught, right. P naught remains constant throughout. We are changing the ambient pressure, right. We are pulling the flow through the nozzle. So, P naught remains constant. For the given value of P naught, I calculate P star from this expression, and when the ambient pressure reaches a value equal to that, I attain this state. Okay. That is the most important point, and the velocity at the exit, let me finish this. So, P ambient reaches this value and P2, which is the exit pressure, is always equal to P ambient. Right. So, as long as we are here on the subsonic portion, the exit pressure is always equal to the ambient pressure. Okay. So, this is always true when m is less than 1 or just at the instant when you reach m equal to 1. When the flow is subsonic, the exit pressure is always equal to the ambient pressure, and the exit velocity u2 is equal to gamma r T star, where the T star corresponds to given value of T naught. So, this is a critical state when we just reach the sonic state from above. Okay. So, in this case, if you look at the flow that comes out of the nozzle, let us sketch this separately. If I look at the flow that comes out of the nozzle, so this is the convergent nozzle, state 1, state 2. So, the jet comes out of the nozzle and the pressure at the exit P2 is equal to the ambient pressure. That means the jet comes out like this. The diameter of the jet as it comes out is equal to the exit diameter when the pressures are matched. Okay. Now, we look at a situation when we lower the ambient pressure even more. Okay. When I lower the ambient pressure even more, what will happen to this flow? The flow in the nozzle, if I lower the ambient pressure some more, right. Let me sketch that separately here. So, we have attained that state, right. So, let us do it like this. P1, T1, P01, T01, this is state 1, this is T star, this is my state 2, P2 equal to P star. Now, I have lowered my ambient pressure to a value even below this. For example, let us say that this is my ambient pressure now. So, the flow has expanded from state 1 to state 2. Will it now expand to this state or will it remain the same? It will remain the same. There is no scope for it to expand to this value, because then what would happen here? If it expands to this state, what would be the Mach number? Supersonic. So if the Mach number is supersonic here, that means it must have gone through the sonic state at some other cross section, right. So we are saying that the nozzle looks like this. So if the flow is supersonic at the exit, right, this is the exit state now. If it expands to this pressure, this is the exit state. So if the Mach number is supersonic here, that means the sonic state should have been accomplished somewhere here, right. This is less than 1. So m equal to 1 should have come somewhere here, which is not possible because m equal to 1 can occur only at a throat where dx equal to 0. So that means it is not possible for this flow to go further down, it will continue to stay here, but the ambient pressure will continue to get lower, which is why we said that once the nozzle chokes, there can be no change in the mass flow rate by controlling the flow from downstream. However, one thing that happens is, because when the jet comes out, P2 is now greater than P ambient. P2 is greater than P ambient, that means the jet is under expanded. It is coming out at a pressure which is greater than ambient, which means it must expand to match the ambient pressure. That is why it is called under expanded, right. So the jet expands outside the nozzle if P ambient is less than P star. Okay. So in this case the jet is said to be under expanded. So what do we mean by jet expands outside? What does it mean when I say jet expands? What happens to the, here we said that the diameter is the same as the exit diameter when the pressures are matched. Now here when I say jet expands, I literally mean expands. So the jet actually swells, right. So the expansion process takes place like this. So the jet actually swells when it comes out. So it expands outside. But it cannot continue to do this. The jet will expand and then it will shrink, and then it will expand again. So it will keep going like this until it finally equilibrates with the atmosphere or the ambient condition. Then the jet diameter will become like this. We will actually, as we go along in the course, we will actually try to evaluate these angles that the jet will make and the places where it contracts. We will look at the detailed structure of this jet as we go along, but this is what happens when you have a situation where the ambient pressure is less than P star. Notice that we are talking about aircraft engines and thrust is what we are ultimately interested in. So when this jet expands against the atmosphere, that is not useful, right. Remember what we derived the expression for thrust. We derived two expressions. One was I2 minus I1. The other one was what? Integral PdA on the surfaces. So only when the jet or the fluid expands against the surface, that results in useful thrust. If it expands against the atmosphere, that is not useful for me, right, that is lost, right, that is not of any use. So how will I make this thrust useful? What can I do? By putting a divergent section here, that is what we will talk about next. If I put a divergent section here, then the fluid can expand against that and produce useful thrust. Okay. So this is the sequence of events when we actually pull the flow through the nozzle. So this is what we are doing when we pull the flow through the nozzle. See, any further reduction in pressure here, we can argue this in many different ways. Any further reduction in pressure is still not possible because of the conditions that we set from area velocity relationship. The other physical way of stating this is, if I reduce the pressure some more, the flow at the exit of the nozzle is already traveling with the speed of sound. Now reduction in pressure is that information is trying to travel upstream, but this is already traveling with speed of sound. This pressure signal is also traveling with the speed of sound, with the result that nothing gets past this m equal to 1 location, which is why the flow upstream of the nozzle is completely insensitive to any changed pressure conditions downstream. That is a physical way of arguing this. Okay? Of course, keep in mind that as long as the pressure disturbances travel with speed of sound, this is true. What if I make the pressure disturbances travel with velocity greater than the speed of sound? I close a valve suddenly, then the speed of propagation is actually much higher, can be supersonic. If it is supersonic, then definitely it can go upstream. Okay, as long as I do this gradually, this is all I can do. But unsteady compressible flows are really not within the purview of this course. Okay, so I am just telling you that it is possible, but that is not something that we will look at. Okay, alright. So what we are going to do next is look at the sequence of events that happens when we push the flow through a nozzle, keeping the ambient pressure constant. Remember, this kind of scenario actually happens in real life. You may wonder, when can the ambient pressure change, right? Ambient pressure is always constant, so why are we talking about this? Think about an aircraft engine, that is what we are going to do next, right? An aircraft engine takes off from sea level, then it climbs to an altitude of 35,000 feet. Definitely the ambient pressure changes, right, from sea level to 35,000 feet. So this is not something which is contrived, this is very real, this happens all the time. If you think about a rocket, it is even worse. It takes off from sea level and goes up to vacuum, almost vacuum in the outer space. So this is something that happens all the time. So this is very, very important. This is very real and very important. The next scenario that we are going to look at is pushing the flow through the nozzle by increasing the stagnation pressure, for example. Okay. So we are now going to look at the next set of next sequence of events when we push the flow through the nozzle. The difference between these two is that here P0 is fixed, P ambient changes, right? Here P ambient is fixed, P0 changes. Okay, we do not really look at situations where T naught changes, that is tantamount to reducing T naught. That is not something that we would want to do. Increasing P naught is not a problem, right? We run a compressor, we can get higher and higher P naught. So that is what we are going to look at. P naught changes or P naught increases, P ambient remains fixed. Okay, so let us look at the sequence of events on a TS diagram. So same way, we have state 1 here and state 2 here. Let us say that this is my this is T and this is my T01. We will assume that T0 remains the same throughout, there are no changes in T01. So this is my T star corresponding to m equal to 1, this is m less than 1, this is m greater than 1. So, let us say this is my state 1. For some value of P naught, I am establishing a flow. So, this is my, so the flow expands. So, this is my expansion from state 1 to state 2. Remember, the ambient pressure is fixed, right. So, when the Mach number is subsonic, the exit pressure is always equal to the ambient pressure, correct. When the Mach number is less than 1, when M2 is less than 1, P2 is equal to P ambient, right. So, I can draw the isobar corresponding to P ambient like this. This is my isobar corresponding to P equal to P ambient. So, you can see that the exit pressure P2 is equal to P ambient in this case. Now, I increase the stagnation pressure, right. So, what happens to the inlet state? Where do I show it? I increase the stagnation pressure. Remember, isobars diverge from each other. So, when I increase the stagnation pressure, I need to move to the left, right. So, I need to move to the left for a, so I operate at a different value of inlet stagnation pressure P01, and so my inlet state may be something like this and my outlet state will be something like this. So, I now have expansion like this. So, I have increased the stagnation pressure. So, I am actually going this way, but the exit state continues to lie on the P ambient isobar. If I increase my stagnation pressure again to a value which we wrote down earlier, P0 over P star. So, if I increase the ambient pressure to a value which is 1.8929 times the ambient pressure, right. So, if I increase my, so this value of P01 is equal to 1.8929 times P ambient. So, if I increase my P01 to that value, then my state 1 is probably somewhere here, state 2 is here. So, we have attained the sonic state at exit, M becomes equal to 1. Okay. So, for example, this can be this P01 can be say 1.1 times P ambient, this is let us say 1.5 times P ambient, this is now 1.8929 times P ambient, that is the critical case, right. Exit state M is equal to 1. Right. The mass flow rate keeps increasing like this. Now, what would happen if I increase the stagnation pressure to a value which is let us say even higher than this, right. So, we are coming along in this direction, there is nothing that stops me from doing this, right. I can increase the stagnation pressure here. What would the state line look like in this case? What would the process line look like in this case? State 1 will continue to be here. What about state 2? Where will state 2 be? State 2 will still be over here. This will be 2 and this will be my state 1, right. There will be no change. State 2 will continue to be in the sonic state. But what happens to the pressure at state 2? Pressure is now higher compared to the ambient. In the previous case also we said that because we were lowering the ambient pressure, we said that exit pressure is higher than ambient pressure. So, the jet was under expanded. In this case, because we are increasing P naught, the exit pressure is once again higher than the ambient pressure and the jet is under expanded. When one quantity, so we take P2 and P ambient, when we say P2 is more than ambient, that can be a result of P ambient decreasing, or it can be a result of P ambient remaining the same and P2 increasing, right. So, for example, if the ambient pressure is equal to let us say 100 kilopascal, right, this could be something like 110 kilopascal, 120, 189.29, this could be let us say 200 kilopascal, So 200 kilopascal exit pressure will be higher than 100 kilopascal. So the jet in this case will become under expanded, right. So when P2 which is equal to P star becomes greater than P ambient, jet is under expanded, same as before. The only difference between this case and the other case is that the mass flow rate continues to increase. In the previous case, once I attained this type of a situation, the process curve did not change, it remained the same, right. So if I draw the other curve for comparison, if you recall, the previous case looked like this. So this was the process curve when we attained the sonic state at the exit, and if I lowered the P ambient, the P ambient curve looked like this, right. So this was P ambient. So if I keep lowering the P ambient, the process curve does not change at all, which means the mass flow rate remains the same. In contrast, here as you can see, the process curve keeps changing. Exit state is sonic state, but the process curve keeps changing, which is why the mass flow rate in this case reaches a maximum and remains there. Whereas in this case the mass flow rate will continue to increase. As I keep increasing this curve will keep sliding to the left and the mass flow rate will continue to increase. That is the biggest difference between this and that. Here after I attain the critical state, the process curve remains the same, I cannot change it anymore by lowering the ambient pressure. Whereas here I can change the process curve by increasing P0 continuously at will. So mass flow rate can also be changed at will as I keep increasing P0. That is the difference between these two. Okay? Any questions? What we will do in the next class is go through the same type of argument for a convergent divergent nozzle. Okay, what happens, what are the sequence of events when we pull a flow through a convergent divergent nozzle.